Well, let's get started. I'm Hart, and today I'll be talking about new attacks and constructions of quantum money. And this is joint work with Jiahui Liu and Mark Zhandry. So let's briefly go over the outline for today's talk. I'm going to explain some background about and define quantum money, and then mention why I think we should care about it. I'll then go over an attack on a general class of lattice-based quantum money schemes that breaks the recent candidate construction of Khesin-Lu-Shor. We'll then transition to talking about a new generic approach for building quantum money, as well as a number of different ways for potentially instantiating this generic construction. I'll say this paper seems to open more problems than it solves, so I'll frequently mention possibilities for future work. And finally, I want to apologize. We're going to employ a wide range of cryptographic assumptions and techniques, and I'm not going to be able to give the background for all of them in this talk. So sorry about that. Let's get started. So what is quantum money? Fundamentally, the main idea is to use quantum no-cloning and cryptography to create unduplicatable, verifiable money. So quantum money dates back to the famous scheme of Wiesner, although public key quantum money, which lets anyone verify quantum banknotes, and which is what we will focus on today, was not defined until Aronson's seminal 2009 paper. In this work, we'll use the popular definition from the Aronson-Cristiano 2012 paper that lets us define and focus on schemes with single banknotes. So quantum money consists basically of two algorithms, a generation algorithm and a verification algorithm. Gen outputs a bill and a serial number, and verify takes as input a banknote and a serial number and outputs a bit indicating verification. And Aronson and Cristiano show that this simple scheme plus signatures allows you to build a full quantum money environment. So let's talk about security. So today I'm also going to define security for quantum lightning, which is an even stronger primitive than quantum money, and which will be our primary focus today. So in a quantum money scheme, an adversary is given a banknote and a serial number and asked to generate two banknotes that verify for that particular serial number. And we say a scheme is secure if there's no efficient adversary that can do this. Quantum lightning, on the other hand, the adversary wins if they generate two banknotes that verify under a serial number of their choice. So it isn't perfectly accurate, but for cryptographers in the audience, I like to think of quantum money as sort of analogous to superposition, second preimage resistance, and quantum lightning as analogous to superposition collision resistance. So why should we care about quantum money? Well, for one, it has the potential to give us great insight into cryptographic proofs. There's a long line of work on rewinding proofs or certain other interactive protocols that are secure in a quantum world, and these are made easier with what is called collapsing hash functions, which are hash functions where it is hard to tell whether or not the input is in superposition. So sort of the opposite of quantum lightning, if you will. So ruling out quantum lightning schemes actually has a pretty big benefit to cryptography. However, building them would be undoubtedly even more exciting. So, here's a graph of the cryptocurrency market cap today, and I know many of you might groan at this, but it's over $1 trillion. And in the very long term, if or when everyone has quantum wallets, quantum money could replace blockchain-based cryptocurrencies and NFTs as the most popular choice of decentralized currency or token. And there are a number of really strong advantages of quantum money over blockchain. It's fully decentralized. There's no need to run any consensus protocols since no cloning solves double spending. It's optimally scalable since there's no need for non-transacting parties to do any work. And finally, it's perfectly private since non-transacting parties see nothing and you don't have to send your transactions to a mempool or a blockchain. And I want to emphasize that this does break Vitalik Buterin's famous blockchain trilemma, which states that no blockchain can have scalability, security, and decentralization at the same time. It might be true classically, but it doesn't appear to be true quantumly. So, although quantum money has potentially huge applications, it has proven so far to be very hard to build. Lots of exceptionally smart people have tried to build quantum money, and about all that we have at this point is candidate constructions without strong security analyses. And in fact, we don't have a single quantum lightning scheme with a security proof that does not involve abstract oracles. So in this work, we show how to build quantum lightning using generic construction, which may have many potential instantiations. So we're also unfortunately stuck using oracles and non-standard assumptions, but the generality of our construction is something that we believe to be novel. We also showed that the recent KLS-22 scheme is unfortunately part of a large class of lattice-based schemes that can't possibly work. And I do want to take a moment here and emphasize that the fact that the authors of this KLS-22 work were exceptionally nice and communicative with us throughout this process. And it was really a pleasure talking with them about quantum money, and they really helped us understand their scheme in detail. So I just want to take a moment and thank them. And finally, we do note that our framework for constructions does address the knot construction, and I'll talk more about this later. So to explain our impossibility result on a certain class of quantum money, it's useful to go back to a lattice-based strawman proposal that Zhandry made in his seminal 2019 paper on quantum lightning, and which he has talked about considerably since then. So we'll start with public parameters that are just a random sort of tall and skinny matrix. And if you're familiar with lattice-based cryptography, which I see many of you in the audience are, you can think of this as a usual LWE or cis matrix. So our gen algorithm is going to sample a distribution of short vectors over the integers. And for now, in most of this talk, we're going to assume this is a discrete Gaussian distribution. Then, in a new register, we're going to compute the cis hash, which is just multiplication by a transpose of this superposition, and then measure the output. And so our quantum banknote at this point is then a superposition over short vectors, such that each of these short vectors has the same cis hash value, or if you want to think about the lattice, they're in the same coset of the lattice. So let's think about security, and let's ignore the thorny part of verification at this point. So if an adversary does manage to create two superpositions over short vectors that have the same hash value mod q, then we can measure these two superpositions and hopefully get two different values for y, right? So recall, and I'm sure that many of you are familiar with the cis problem, that the cis problem asks us to find short vectors that are in the kernel of A transpose for a random matrix A. And so if we have two vectors that are offset by the same amount, in other words, they have the same hash value, we can subtract them and get a vector that solves the cis problem. But this only helps us in the case of an honest adversary, right, that actually generates these colliding superpositions. What if an adversary gives us two classical states with the same value of y? This obviously won't work. And in this case, we'll actually be in trouble. But let's explain how a verification approach might work. We could apply the QFT to our superposition of vectors, and as shown in the famous result of Vregev, get a superposition of essentially LWE samples. If we had a magic LWE distinguisher that didn't corrupt our money state, we could use it to verify that the state was in the correct superposition, and then return the state to its original form. Now, note that classical states wouldn't pass this test, since the Fourier transform wouldn't result in LWE samples, and in general would not have its mass concentrated close to lattice points. So to handle this, Zhandry proposed a problem that I'll call testable LWE. And we could get around this sort of verification dilemma in the following way. What we really want to do this is a method of sampling our LW matrix A. Maybe it's not uniform, and maybe it also has some auxiliary information. So first, we want the cis problem as we defined before to be hard, and we kind of have it graphically displayed up here. We also want search LWE to be hard. For those of you that are familiar with lattice cryptography, you probably know what search LWE is, but in general, it's the problem of given a random column vector in the span of A, plus a little bit of noise, find the close vector in the column span of A. And it turns out that, due to a result of Vregev, we basically know that search LWE and cis are almost equivalent problems. Now, the really interesting thing we want is we want decision LWE to be easy. And decision LWE, right, is given a random vector in the column span of A plus some noise, distinguish that from a uniform vector. And this is going to be information theoretically distinguishable if A is sort of tall enough, but we want it to be efficiently distinguishable. And I know some of you are already thinking, well, Hart, isn't there a search to decision result for LWE? Doesn't that, obviate this scheme? And the answer is not exactly. The search to decision reduction only holds for uniformly random A, not in the presence of auxiliary information, and it randomizes the matrix A in the process of the reduction. So it's entirely possible that this sort of candidate construction could in fact exist. And so the basic idea of the KLS-22 construction, and I emphasize that this is our interpretation of their instruction, essentially works as follows. the authors use Zhandry's lattice proposal in disguise with a twist. They provide 3 short vectors with a special structure in the kernel of A transpose. And the idea, and it's a clever one, is that these short vectors can be used in the verification process, since intuitively decision LWE will be easy. However, it's also the case that, search LWE, as we discussed earlier, will be hard. So unfortunately, there's a problem with this approach. While the S vectors will let us distinguish between random samples and LWE samples, they will not let us distinguish between properly drawn LWE samples and samples that are essentially uniform in the kernel of these S vectors, plus a little bit of additional noise, and this is something that we prove in the paper. The intuition is sort of as follows. If we let A bot denote a basis for the dual lattice of A, or the integer dual lattice, then we can efficiently sample a forgery distribution using the S vectors because they're short, which gives us this fake LWE distribution we mentioned in the last slide when we apply a QFT. Now, the real superposition, QFTs to an LWE distribution, that we claimed in the last slide was indistinguishable to the fake distribution above, which is intuitively why the scheme is broken. Now, this intuition is obviously not a full proof, which takes a bunch of additional formalism, but we sort of proved that this strategy works in the full paper. And to fully complete the proof requires a bunch more steps. So first, we have to translate KLS22 to sort of Mark's lattice-based framework, which is not so easy. And we end up having to actually show some pretty interesting new results. So we show that cis is collapsing for polynomial modulus, which improves the result of Zhandry 19, who showed that it was true for superpolynomial modulus. We also have to extend known results on the KLWE problem, for those of you that are familiar with lattice cryptography, to make it hold for sort of a more arbitrary vector distribution. An open problem here is I think Zhandry's testable LWE idea is really interesting. A new quantum money scheme would be fantastic, but even if you could rule this approach out, it might have other positive impacts on lattice-based cryptography, since you'd essentially be tightening the LWE search to decision reduction. So it's easy to be pessimistic about the feasibility of quantum Lightning at this point, particularly if you want to build it from standard cryptographic assumptions. And the rest of this talk in this paper, we put together a generic Oracle-based construction that seems to have many different possible ways to be instantiated. And while none of these schemes are from standard assumptions, and some are unimplementable in their current state because they use oracles, we hope that they can be steps towards quantum Lightning for more standard assumptions. And we'll spend the rest of the talk going over this. So our generic construction is what we call a walkable invariant. So we have a set X with subsets O and a set Y coupled with mappings with some special properties. We have an invariant mapping I that maps X to Y, and we have a bunch of permutations on X, which we refer to as sigmas. And I don't want to get too formal with this, but it's all formally done in the paper. So importantly, we require that I maps every element in a subset O to the same output, and also that the sigmas map elements in a particular subset O back to that same subset. And, so the sigmas sort of look something like this, and I may refer to these as orbits in the future because that's sort of what they are algebraically, and that's what they are when you really get under the hood. So how can we use this structure to build quantum Lightning? And I sort of have the structure on the left. So our construction turns out to be pretty simple. We're going to sample a superposition of all elements of X, and we're going to compute the invariant I in an additional register and then measure this output. So you can sort of see how this is very similar to the lattice construction, at least in this approach. And our banknote is going to be the superposition, and our serial number of the quantum money is just going to be the output of this invariant. And I want to say, for verification, it's actually a little bit more complicated. We're computing sort of an approximate self-projection that essentially uses the permutation to randomize the superposition and check that it's still the same, which it should be for correctly generated money. And this is an idea that's borrowed directly from the quantum money from Knott's paper. And in this work, we prove a theorem that shows our verification process works, sort of if the permutations mix enough. So our construction needs 2 assumptions for security, which we call the hardness of path finding and the knowledge of path assumptions. So the path finding problem is essentially an analog of discrete log modified to our setting. So given two x's, or set elements, find a path of permutations between them. So we emphasize that while discrete log is obviously itself easy quantumly, certain analogs like group action discrete log are not, and we'll go over this a little more in just a couple of minutes. So the knowledge of path assumption is substantially more complicated. So very informally, it says that if an algorithm outputs two x's, then there's an efficient extractor that can output a path between them in terms of the sigmas. And this is sort of a quantum variant of knowledge of exponent assumptions, if you're familiar with those. And I'll say that the hardness of path finding is generally very reasonable for our schemes and boils down to standard and well-studied assumptions, while the knowledge of path assumption is very magical and needs a lot more study to have confidence in it. So a little bit of intuition about the security proof, and it's sort of complicated, so I can't really go into it too much here. But in the paper, we show that any scheme in our model that satisfies the hardness of path finding and the knowledge of path assumptions gives us a secure quantum lightning scheme. So, we first claim for some intuition that verifying quantum lightning states must include sort of whole subspaces, and this is true because otherwise the permutation you can easily see that it fails. An easy case is when the adversary sort of gives two non-negligible weights on a desired subset, and we can, relatively straightforwardly use our knowledge of path extractor here. A harder case is when the adversary gives us two lightning states with no weights on any orbits that are interesting to us for our reduction. We have a pretty subtle proof. I don't want to go into it too much here, but if you're interested in this, I'd encourage you to read the paper. And I like to think of this as sort of a quantum collision resistance to one-wayness reduction. So again, this knowledge of path assumption is very interesting and sort of a novel quantum assumption, and it definitely needs more study. It could be that it's just not true for a number of applications. So the first scheme that we mentioned that potentially falls under our framework is the well-known quantum money from Knott's paper. So in fact, this scheme was the inspiration for our generic construction, and we wanted to simplify it and understand why it worked. And while we can prove it's secure modulo some assumptions on knots, these assumptions are quite strong, and I'm not a mathematician, but it seems like proofs would probably advance knot theory. So please see the paper for details. We don't even have time to define knots here. So our next instantiation is from cryptographic group actions, and unlike knots, group actions are simple enough that we can present almost everything we need on a single slide. So as many of you know, a group action is a tuple of a group, a set, and a mapping that satisfies the identity and the composability properties. And composability is just sort of like associativity for groups. These have a long history in cryptography, and for now we're going to assume that we have sort of an ideal group action, which is called an EGA. And, like classic analogs, we can also define hard problems on group action. Like this is the group action discrete log problem, which is exactly what you'd think it would be. So let's consider an instantiation of our generic scheme with group actions. So we sort of had group actions in mind when we were writing down the scheme, so the instantiation is actually quite similar. So first, recall the generic construction. And now let's look at the group action construction. So the banknote generation of the protocols is extremely similar. I'm going to gloss over the invariant right now because we'll need an oracle for that, although it is actually a natural thing for some group actions, and we won't need an oracle. The verification processes are also extremely similar, and we can view the computation of the group action as sort of a permutation on the set. So I will say, though, that the description of the scheme hides a number of tricky caveats, unfortunately, most of which are around sampling set elements and the group action structure. But modulo these things, we can prove security for a generic group action, which if you're familiar with that, it's just a sort of natural extension of generic groups to group actions. So I think a really nice open problem is, does the knowledge of path assumption hold for generic group actions? So classically, we know that the knowledge of exponent holds in a generic group model, but does the quantum analog hold? Now, you might not be surprised that if we're claiming a construction of our protocol from a group action, we also claim a construction of isogenies. since many isogeny protocols can be viewed as group actions. And I'll briefly sketch a protocol here, although I obviously don't have time to formally define isogenies and everything like that. Recall that an isogeny is essentially a mapping between elliptic curves, and notably, isogenies only map between curves with the same number of points. So the core idea is to let our set consist of elliptic curves with some related structure. We let our invariant be the number of points on the elliptic curves, and then we sort of use the isogeny computation as our permutations. And you can sort of see, right, like the hardness of pathfinding boils down to inverting the isogenies, which is the core problem in isogeny-based cryptography. So there are a few outstanding problems to make this work. We have to assume it's possible to efficiently obliviously sample elliptic curves, which, we have some stuff in the paper on this, but this is not known. And the knowledge of path assumption is obviously not standard for isogenies. So, this whole construction of potentially building quantum money from isogenies is really open, and making at least our construction work would involve new sampling techniques for isogenies that would be quite useful for many other applications as well. So finally, the last construction that I'll mention today is a construction from functional encryption. If you're a cryptographer in the audience, you might assume that with some special form of functional encryption, we can get this sort of quantum money. But unfortunately, we need a new non-standard version of functional encryption that we don't know how to build, even from I/O, and we call this re-randomizable functional encryption. And sort of the abbreviated requirements, we have a full version in the paper, is we need oblivious ciphertext sampling. We need the ability to have a functional key that outputs a collision-resistant hash computed on the encrypted value. And we need a re-randomize function that sort of perfectly re-randomizes the ciphertext. And it's a little bit tricky to handle the randomness quantumly, so I'll encourage you to see the paper for that exact requirement. But with this in mind, the construction, outline at least is sort of relatively simple. So we sample a superposition of all FE ciphertexts under certain public parameters. We compute in superposition and measure the output of the map of the ciphertext computed by the functional key, and this gives us the CRHF evaluated on the plaintext, and then we output the banknote, and the CRHF output is our serial number. To handle verification, we use sort of the re-randomized functionality of the FE to implement a similar projection as before. And I will say that precise requirements are tricky, so please see the full paper for details. Obviously, an open problem is, can we build this notion of re-randomizable functional encryption from even powerful primitives? We don't even know how to build quantum lightning from I/O or really anything else that's not an oracle, so this would be a step forward. And with that, I'd like to conclude and thank you for your time and ask for questions. Whoever, sure.
So thanks for the nice talk. For knowledge of exponent assumptions, it is my vague understanding that basically they're there for efficiency. Like if you can build something with them, you can also build the same thing without them at the expense of the primitive being constructed in a more expensive way. So I'm wondering basically what the bottleneck is of like, applying similar techniques in the setting of quantum lightning. Is it the fact that verification needs to be non-interactive, or what's the bottleneck? So yeah, certainly verification being non-interactive is a big bottleneck. If you allow interaction for verification, then you can have much simpler schemes. And there are papers that go into sort of all these different definitions of quantum money, and you can relax things. And I really didn't go into that in the talk today, so sorry about that. But you're right that if you relax things and allow communication, you can sort of, you could really simplify the protocols and build them more easily. As far as the classical to quantum comparison of like the knowledge of exponent versus this knowledge of path thing, I really don't know. So we use the knowledge of path assumption in the proof in a way that I've never seen sort of a knowledge of exponent assumption used in the proof. So it might be something that's just totally different quantumly, even though it seems sort of very, syntactically similar. Thanks.
So if I understood correctly, so you propose this general framework of walkable invariant and then showed that if it satisfies these two security properties, then it applies quantum money, right? So if you try to fit in the KLS construction into this framework, which of the two security properties are violated? I mean, I can think of this O as being the set of all short solutions, I being the map that maps this matrix times this short solution to be Y.
Yeah, so it really, which security property doesn't work?
One of them has to be violated, right? Because you show that the scheme is insecure.
Yeah, so it depends on the verification algorithm, I guess. So I think in their particular instantiation, it would have been the knowledge of path assumption. But sort of what we show here is that there's no verification algorithm that can work. So it's a sort of difficult question to answer. So if you're saying that like something doesn't work, which assumption doesn't hold, it sort of could be either, I guess. Sorry for the...
One other quick question. So my big understanding was that the NOT-based construction did not satisfy correctness because the verification, we didn't know whether it could be implemented in polynomial time. So how are you able to sort of fit that construction into your framework?
Yeah, so I think I said it in the slides, or maybe I had it in the slides, but I didn't say it. But we have to assume that, I think I had it as an open problem actually. We have to argue that, we have to assume that there is a mixing algorithm that works, and we go we explain this in the paper about what precisely we need for a mixing algorithm to work. But we need the mixing algorithm to work, and we need it to work in polynomial time. And this is an assumption. We don't know whether it's true or not on the NOT construction, but we have to assume it for security. You're exactly right.
Thanks.
Can I? So one thing that was not clear to me, like these childs at all. No, oh, for this, does it say something about your reduction? Is it even a good result?
I don't think so. Certainly not at a topical level, but I'm not going to claim to understand that paper on like a super, super deep level. I think, again, looking into this knowledge of path assumption and sort of what it means quantumly is a great open question. I'd love to see a talk from you here next year on that.